Good day, everybody. There are many different types of technologies used to beneficiate like fine iron ore. We have cyclones, we have spirals, we have magnetic separators, as well as classifiers. For these different technologies, each technology has like its pros and cons. These pros and cons also have a direct impact on efficiencies and also the profitability of the operation. Therefore, when making a selection, the right choice matters. So with that said, now the question is, why choose the spirals instead of like other technologies? This is the basis of the presentation today. This is the outline of the presentation. I'm going to do a brief overview of the iron ore flow sheet and also discuss the different types of iron ore we have on the Multotec spiral range, and also end off like with a couple of case studies on the spiral circuits. This is the typical iron ore flow sheet. It has three main sections. The first section there, that's your crushing and screening. On there, the coarse and the fine material is screened and separated. The coarse material goes to the coarse DMS section, and the fine material is sent to the fine section. On the fine section, the material is further split into two portions. The one portion is sent to the fine DMS, and the fine material goes to the spirals. The spirals typically receives like -1 millimeters. As previously mentioned, in addition to spirals, there are other technologies that can be considered in place of spirals. Now, the question is, why choose spirals? These are some of the benefits of utilizing spirals. So spirals are simple, low energy consuming devices. The only thing that requires power really on the spiral is actually the pump that delivers the feed to the spiral. The spirals separate minerals mainly on the basis of density. They have no moving parts, and therefore you can actually expect to do less maintenance on them. They also use water as a medium. Unlike your DMS or flotation, you don't need to actually have reagents. And then this also save costs. And then therefore, we believe that spirals are cost and metallurgically efficient. On this section, I'm just going to discuss the different types of spirals that we have like at Multotec, and also show you the different ones we use like for iron ore. We have over 10 different types of spirals, like different shapes, different heights, and diameters. And then these spirals can also do various throughputs. We have the spirals that we consider the standard iron ore spirals. These spirals, the SC20 and the SC21s. These spirals, they're small in diameter. The diameter of these spirals is around 600 millimeter. The ideal size fraction for processing on these spirals is a -1 millimeter plus 45 micron. The maximum throughput that you can put on these spirals is around 2 tons an hour per start. For material that's a lot finer, with the top size of about 800 micron down to 45 micron, our preference is to utilize the HX5. The HX5, it's a fine range spirals. Unlike the smaller diameter spirals, the HX5 and HX3, they're large in diameter. So the HX5 and HX3 have the same profile. The only difference is the number of tens. The HX5, like the number says there, it's 510. Whereas the HX3, like the number there, it has 3 tens. So the HX5, it's around 1 meter in diameter, and it can actually process up to 5 tons an hour per start. Recently, we've added like another spiral like onto our spiral range. We call the spiral the UX7. This spiral has specifically been developed to handle the ultrafine material. We know it does not matter like what mineral is getting processed, like there's an issue with ultrafine. So the UX7 is ideally suited to processing the material with a top size of about 100 down to 10 microns. The UX7 has a similar diameter to the HX5. It's around 1 meter. And it can also do up to 5 tons an hour of throughput, again, per start. For difficult or complex or difficult to separate ores, in particular where there are challenges with coarse silicates. Coarse silicates, I'm talking about a particle size of above 300 micron. We typically utilize the wash waters onto the spirals. The wash waters, number one, they help with increasing the fluidity and to number one, eliminate the bleaching. Number two, if we don't have wash waters, the coarse silicates tend to behave like heavy material, and they would actually come closer to the center column here, where you're supposed to only have clean iron, and they will contaminate that stream. However, applying the wash waters helps to wash away these coarse silicates and therefore enhance grade. We have two different types of wash water systems. In this particular case, this is the high flow. On the high flow system utilizes about 21 liters per minute of wash waters. On the drip system, this is the second system that we have. As we all know, like water is an important commodity. As a way of us optimizing the wash water rate, like we developed this drip system. The drip system utilizes a low flow. Up to 5 liters per minute can be utilized like on the drip system. So on this section, I'm going to share two scenarios. It's 2 circuits, and this would actually demonstrate how we can actually configure the spirals in a circuit to achieve the desired product specifications. So depending on the desired product requirements, more than one stage can actually be employed. In this case, we tested a 3-stage, and with rougher, cleaner, and a scavenger. Prior to processing on the spirals, the material was deslimed. I also would like to mention that this was a hematite ore. It originated from India, and the customer required a product with an Fe content that is greater than 64% and a silica that is less than 1%. Like I've mentioned, after desliming, the material was processed on the spirals. For this particular configuration, a combination of the HX5 and AC21 spirals were tested. The HX5 was tested for rougher and scavenger, and the AC21 spiral was tested for the cleaner application. So these are the results for that corresponds directly with the flow sheet I've shown like in the previous slide. As you can see here, the head grade of the material was around 58, feeding the cyclone. So the spirals managed to do an upgrade to 67% Fe. Similarly, on the silica side, we had about 5.5% silica in the feed, and that was downgraded to 0.5%, like in the cleaner concentrate. And then if you were to compare it like with the product specification as previously stated on the previous slide, the final concentrate met the customer specification. And this was achieved at a mass yield of about 45% and a recovery of 52%. So in this scenario, we can see that the spirals can actually be configured on their own, like utilizing multiple stages to meet customer needs. So this is a second configuration. So for complex material or where the ore is difficult to separate, like spirals can be paired with other technologies to, number one, enhance the grade and also like improve the recovery. In this particular scenario, the spirals was paired with the magnetic separator. So it was actually a 4-stage in total. 2 stages like were utilized for the spirals, a rougher and a cleaner. For the rougher, the HX5 was again utilized. Like I've indicated that this was a complex ore with a high concentration of silica. And then in this particular case, the SC20 high capacity with wash water was tested to try and then clean out the coarse silicate. For the scavenger, the WIMS and was utilized. The WIMS was utilized for the scavenger, as well as the recleaner. So just a little bit on the flow. The rougher tail, together with the cleaner tail, was sent to a primary WIMS to do the scavenging. And because the product from the cleaner was not at the desired product specification, the concentrate from the primary WIMS was combined with the cleaner concentrate and sent to a secondary WIMS for further cleaning. This next slide shows the mass balance of the previous flow sheet. As you can see here, the iron in the feed was around 37%, and the spiral upgraded to around 66%. In terms of the iron, the spiral did actually meet the desired product specification. However, because this material had high concentration of silica at 38%, the spiral up to the cleaner stage only achieved or could only downgrade it to around 3.75% silica. As you can see, comparing it with the product requirement, the silica was still a little bit on the high side. But after employing additional 2 stages of WIMS, the iron was further upgraded to around 67%. And the silica was further downgraded to around 2.19. Although the silica was slightly above 2.19, like it could actually be optimized to be in line. So like I've actually alluded to, like in the beginning, for this particular case study, the addition of the MagSep onto the spiral circuit had like some benefits. If you actually look at the mass yield they achieved on the cleaner, it was around 23. But if you add on the concentrate, like from the MagSep, we could actually improve that yield to about 28. Similarly, you can see that there's been an improvement in terms of recovery. On the cleaner concentrate, the recovery was sitting at 42, but overall, incorporating the MagSep, the recovery improved to about 52%. So in conclusion, on this case study, it can be seen that the spirals can actually be paired with other technologies to successfully enhance the grade as well as improve the recovery of the overall circuit. So in conclusion, if you are looking for a technology that is simple to operate, low energy consuming, no moving parts with less maintenance, and low operational costs, the spiral is the right technology for you. Thank you so much. This is the end.